Hey seniors, this is my take through in this video, so I hope it's the best one yet. So this objective, I'm trying to get you more familiar with what I just made up as high volume functions and values. I say high volume because they have been and they will keep showing up a lot in Khan Academy, and they are functions and values that as calculus students you are expected to be familiar with. I'm trying to help you get a little more familiar with them in this video. I want to start with breaking down the functions we're going to look at. So all these right here, we're going to explore a little bit deeper in this video. And just a heads up that sine, cosine, e to the x, and the cube roots, I'll put the stamp there, the cube roots of 3 are all continuous functions. They have no discontinuities, and they're defined for every x value on their domain. And then a reminder, I can write the cube root of x as x to the 1/3 power. All the other ones have some discontinuity. So tangent of x has a discontinuity at every pi over 2 and then additional pi interval, which we'll explore. Natural log and log of x are continuous for all values where x is greater than 0, but they're not defined for x is equal to 0. We'll talk about that in this video too, just to show that off. So like, oh gosh, undo that. So again, for both of those, as long as x is greater than 0, they are defined for all, they're continuous on that range. And then x is only, square root of x is defined and continuous for all values where x is greater than or equal to 0. We'll explore that first. There's a little heads up, the natural log of 1 is 0, and the natural log of 0 is actually an undefined value. We'll explore why that is. And one thing I should have included, which I'll include right now, is if we have just the log of 1, that's also equal to 0. And if we have the log of 0, that's also undefined. We'll explore more about why that is in this video. I'm going to share my Desmos screen, which hopefully you can now see. I'm going to clear everything here. So really quick intro into cube roots, square roots, and what e to the x looks like. So if I have the function f of x equals, if I do sqrt on Desmos, it gives me the square root function. Here's your square root of x, a function you all are familiar with, or at least the idea. It's asking what number times itself is equal to me. So that's why square root of 4, we can see right here, is clearly defined as 2 for the output. 2 times 2 is 4, etc. The reason it's only defined for positive values, for positive x values, is because the square root of -4 is asking an impossible question. It's asking what number times itself equals -4. There's no number in the rational number system. If we went to imaginary number system, we could do that, but that's why there's no values defined for negative x values, only for positive x values. Now what's interesting is if we look at the cube root of x, which again, I should do one reminder before I show that off. Reminder that I can write the square root of x as equal to x to the 1/2 power, and these are the exact same function. So if I'm looking at either of those representations, the exact same function. And now if I'm looking at the cube root of x, notice how it's defined for all x values because the question it's asking is answerable for all x values. So we have 8, 2 clearly defined because it's asking, what number times itself equals 8 3 times, and that's 2 times 2 times 2. And then similarly, we have -8, -2 on the function because it's asking what number times itself 3 times equals -8. That's -2. So if we have 3 negatives, we can get to another negative value. And a reminder, I can write this as x to the 1/3 power. Those are the exact same. One big key point I want to touch on really quickly is if you're wondering like when are square root, cube root, when are they going to be defined just for positive x values or all x values? It all has to do with the denominator of the fraction in this rational function. So if I have this, for example, f of x is equal to, yeah, I like that example. Do I? And I'll use it for now. To the 3/5 power. So this is defined for all positive, negative x values. And I knew that because if your denominator is an odd number, it's going to be defined for all positive and negative x values because it's going to be possible to have a negative value that results in that answer. Just so you know, again, I could write that as Desmos has these really cool functions. So I go to miscellaneous and I go to a root like that. I could say x to the third power with the fifth root. Notice how, again, these are mathematically the exact same function. If I have that odd denominator, I'm going to have all positive and all x values as part of this function. And just a really cool reminder about what this question is asking, I'm going to get all the way over here. There are not many whole number points defined on here, but 32, 8 is, because what that's asking for the cube root, it's asking, okay, what number, if I cubed it, would equal a different number that was being multiplied by itself 5 times. And in that case, the only number that's like a whole number that's really clear to find is 32. If I input 32, I get out 8. So if I do 32 to the third power, I get 32,768. And if I do 8 to the fifth power, I get the same value. So it's asking what number, if I were to cube it, would equal another number if I were to raise that to whatever the root power is. Now, on the flip side of when are values defined, if I had, for example, f of x is equal to x to the 5/2, as soon as you recognize or see that you're going to have an even number in the root, that's going to be code for, okay, I'm going to have only this function defined in the first quadrant where x values are positive. I think in the first quadrant, right, but definitely where x values are positive. You can see that if I flip this and made it x's raised to the 2 divided by 5, because it ends in an odd denominator, you can see it's defined for positive and negative x values. The quadrants aren't always the same, but that's going to be your code for where is it going to be defined. Is it continuous for all values of x? So last thing I'm going to show off on this slide, before I get into a little more notes, is this function e to the x. Now you all don't know this yet, but this is probably the most unique function we'll deal with in calculus because its derivative, which you haven't learned yet, derivative refers to the slope of a function at any given point. Its derivative is the same as itself. And its integral, which refers to the accumulated area under a curve, is the same as itself. So this derivative and this integral is itself, and that's, I believe, the only function that it follows that pattern for. I want to give you a little more notes on where that comes from. All right, there's two things I want you to know, and one is that e is a number, it's a value. It's this irrational number right here. It's also referred to as Euler's constant. But if you type it into your calculator, if you hit second, the blue button, and then the division sign on your graphing calculator, you would get e to pop up, and it's roughly this value, 2.718. I also want you to know that it's not random. It comes from a very specific place, which I'm not going to get into in this video, but I am going to link to videos that do a really good job explaining it. I think it's fascinating. I really encourage you to know about like where numbers and values and proofs come from. That's when I always feel like I understood math the best, is when I knew the rationale behind stuff, not just memorizing. But for this video, I just want to introduce it briefly. And it comes from this limit that has to do with exponential growth and continually compounding interest. Again, watch the videos. They give really cool explanations about how that number actually makes sense and how it exists and applies in real world settings. But for this, I want to transition into this idea of a base system. So our number system is written in what's called base 10. So imagine you're seeing this 183 right here. I want you to think of it as money. So if you had $183, if you wanted to express that same quantity in the base 2 number system, which is the system that computers are coded in, $183, that quantity is written as 10110111 in base 2. Again, if you want to learn more about the base system, ask me. It's actually pretty simple and really interesting. But let me go to the next slide. Here's why it's relevant to this video, because of logarithms and how that relationship is established. So just to give you a little dive into our number system, if I wanted to give you an idea of why 183 is represented how it is, and why it's called like the base 10 number system, is the bases refer to each next place value in a number system. So our system is written in base 10 because the first place value is written as 10 to the 0, that's a 0. And then as you want to go to the next place value, you're still using the same base number of that number system and just raising it to the next exponent in order to get to the next place value. And so this makes sense because 10 to the 0 is 1. So this is us saying we have 3 ones, which has just a value of 3. This is saying 10 to the first, which is 10. you're saying you have 8 tens, so that value is 80. And then next you have 10 squared is 100, so you have 100. And so if I add it up, 100 plus 80 plus 3, like I have 183, and that's our base 10 system. You can have infinite base systems, and they're used in different fields of study. The reason this is relevant is because if we're talking about a logarithm, it actually just has a very simple relationship. One, if you don't see a number written under the log, you should, it's supposed to be an arrow, you should assume, let me go back and do it better. If you don't see a number written right here, then the assumption in math language is that it's written in base 10. It's the most common system that we'll use, I believe, in calculus. Now, what this is asking is it's a very particular question, just like a square root or a cube root. So if you're being asked, what is log of 5? Well, just like how square root was asking, hey, like, I wonder what number times itself equals me. Log of 5 is asking, I wonder 10 to what power would result in the number 5? And it's asking that same question on repeat. Just to show you, we can actually get to that answer. It's gonna have some mess in there. I trust you'll to ignore the mess. If I typed in my calculator, log of 5, it's that decimal value you're seeing right there. Because if I answered the question 10, I wonder to what power it would roughly equal 5. It's 10 to this, and if I kept typing all the digits, you would see eventually it would get right to 5. And that's what a log's asking, and that's the relationship established. It's taking its base, and whatever the input you give into it, it's just wondering, okay, what would the output value be that I'd have to raise the base to that exponent to result in that value. So let me go back to these slides, and that's what you're seeing in this setup right here, the y equals log base b of x. Whatever base you're in, it's asking that same setup of, okay, take your base, raise it to the answer you're looking for, like the exponent you're curious about, and that's the relationship that equals the x value you originally input. Cool. So I like to set it up as log base of like the answer is equal to the exponent. So again, if I had an example of, log of 12, I don't see a base written, so I assume it's base 10. So it's asking the same question of, okay, here's the answer I'm looking for. I know I'm in base 10, and I'm curious about what would the exponent have to be, 10 to what power would result in 12. And so I just got to figure that out. That's what log is programmed into your calculator as. It's answering that question over and over again. I'm going to clear all these drawings, go back to my Desmos real quick, and just give you one more example of if I had log of 12, it's that decimal value because 10 raised to, you get the idea, if I wrote it all out, it would be exactly 12. It's like that's the relationship. And so let me show you some examples of actually graphing log functions. So if I had y is equal to log of x, here's what you're seeing right here. It's a very flat function, which makes sense because we're asking over and over again based on the input, 10 to what power equals 6, and so it's 10 to about the 0.778 equals 6. If I had over here, 10 to what power equals 14, and it looks like it's about, my mouse can get there, 10 to about the 1.146 equals 14, because again, we're in log base 10 if you don't see a base written. And one number that makes a lot of sense is right here. I believe in you, mouse. 10 comma 1, because that question, what's being asked there is, okay, I wonder, 10 to what power equals 10, and that has to be 1. And that's why the point 10 comma 1 is directly on the function. And that's why it's a very flat function. It's hard to get to a next input value. You don't have to raise 10 to a very big exponent to get to 16 or 30, et cetera, et cetera. Now, what's really cool with Desmos and just with bases in general is that I can write in any base system. So if I wanted to write in a different base, I'll go to functions, go to miscellaneous, and this little log arret here. I should have written this below, but I can copy and paste it. And so now I'm going to show you if I have y equals, I'll say the log base 2, if I can get down to 2 of the function x, you'll notice is a little bit less flat, a little more, I guess, steep. But I want to show off like what this is saying. So like right here, the point 4 comma 2 is clearly defined because any log base is asking that same question setup where it's asking this. It's saying, okay, log base 2. So it's saying, 2 to what power would result in whatever I input, and I just input 4. So I know that 2 squared equals 4, hence why the point 4 comma 2 is directly on that function. And this is where we get back to the function e, where e comes into this very unique function, where if I write in base e, that's this function right there. Again, e is about 2.7, asking the same question. 2.7 raised to what numbers would result in whatever the input is. This is also referred to as the natural log. They are the exact same function. Natural log is shorthand for just log base e. So that's a big key point, that they come from logical values. They're not random. And what these all have in common is a few things. Notice how they all have the point 1 comma 0 defined. And that makes sense for every single log because that question would be asking, again, 1 comma 0 will be asking, I'll take, base 2, for example. Be saying, okay, 2 raised to what power would result in 1? So that's where x is 1. The only way to get 1 from a base, from a base would be to raise that base to the 0. And so if your base 10, 10, so what power equals 1? It has to be 0, no matter what base you're in. To get to the output of 1, you have to raise, that base to the 0 power. So they all have that point in common. The other thing they all have in common is, I think this will be able to show it off if I scroll down on my Desmo slide. But if I start to kind of follow these functions down, let me see if I can zoom out a little bit. If I follow these functions down to where x gets closer and closer to 0, let me see if I can do it on the blue function. Notice how you see the point 0 comma undefined. None of these functions are defined for where x is 0 because that is asking an impossible question. It's asking this question. So I'll take log base 10, just for example. So if I had 10, I'm asking the same question, raised to, I wonder what would equal, well, if the input was 0, that's an impossible question. 10 to, there's no number we can think of, is going to result in 0. If you're thinking like, oh, like why not negative numbers? Remind yourself that a negative number is just defined as the reciprocal with a positive exponent. So it's a very tiny number, but it never gets to 0. So all these numbers just like dive down to as you get closer and closer, to where x is 0, because that's an impossible question. So every log-based function is defined for positive x values and never where x is exactly 0. Okay, so thanks for sticking with me. Now, there's more in the video, but I want to give you the choice. So we went over the big things I wanted to hit on that maybe you were a little unfamiliar with. If you feel good about your understanding of the unit circle and your cosine, sine, and tangent functions, you can stop here. I trust your judgment. If you're like, I could use a review, I'm curious, then follow along. I'm going to explain a few things about those functions and make you feel a little more confident about tangent in particular, okay? Get my annotation tool. What I have here is just the unit circle, and I have the values defined in quadrant 1 for your cosine and sine values. I put all your cosine values in that lavender color and all of your sine values in that blue color. Now I want to show you and remind you about where these functions come from. They're not random, like they're very logical. And it all comes just from the ratios of right triangles that we've organized into this unit circle. Whenever we go to graph these functions, these sine waves, these cosine waves, these cosine functions, and really it's just the cosine function, waves do look like those functions. We usually start with the main quarterly defined values, so pi over 2, pi, 3 pi over 2, and 0 or 2 pi. And so for cosine at 0 is your x value, it's your x distance. And so it's defined right there at 0, 1. At pi over 2, we haven't gone left or right on the unit circle. And that's why at pi over 2, your cosine value is 0. At pi, we're out to -1. So I'll put a little red dot on the screen right there. I want to make sure that I'm still recording. I think I am. Okay, sorry. I just wanted to make sure that I wasn't just talking to nobody. All right, back to where I was. And then 3 pi over 2, again, we're at 0 because cosine hasn't gone left or right down here, and then back to 2 pi, we're up top. Now, it's not just like an absolute value v, like it actually is a wave in that process. And to give you a few more exact values, I'm going to define really quickly, this will help out with tangent later on. Right there, if I was halfway on the way to pi over 2, that's pi over 4, which is this radian value right there. And I'll say right about there is pi over 6. And then roughly right about there is pi over 3. So to give you a few more cosine values to get a sense of how this wave looks, at pi over 3, we're right here halfway because cosine's 1/2. And then at pi over 4, we're root 2 over 2, which I believe is roughly 0.7. I'm not entirely sure. Yeah, it's roughly 0.7. So it's a little bit higher right about here. And then cosine at pi, at pi over 6 is root 3 over 2, which is about 0.8. And so notice how like they're really close to 1. That's because it actually does move in a wave fashion. If I follow this up best I can, it's kind of close to the peak, and then it kind of dips down real fast, and then it kind of makes, again, like a peak, like a wave, kind of incorporating those circles in here. And there's your cosine function. It just keeps on repeating over and over again. Similar for your sine function. When sine is 0, and those are your y values across the unit circle, starts right here at the origin. At pi over 2, we hop up to +1. At pi, we hop back to 0 because we haven't gone up or down in the unit circle. At 3 pi over 2, we're at -1, which is, I'll put a dot right in the middle there at -1. And then we're back to here, and it kind of follows that same wave pattern where the points are kind of high up towards, the y values get high up towards those quarterly values, and it kind of keeps, it's a very rough wave, but I hope you get the idea. That tangent is fascinating. Tangent reminder is, I should have done this beforehand, but I didn't, it's fine. Tangent is defined as the opposite over the adjacent side. And so I'm drawing in this first pi over 6 radian value. The tangent is going to be your blue side, your opposite side, divided by your adjacent side, which is your sine divided by your cosine values. And so I'm going to define those as quickly as I can, just some tangent values. And so right at 0, if I want to figure out what tangent is, I need to divide my sine divided by my cosine value. So 0 divided by 1 is just 0. I'm at pi over 2 right here. Really quickly, I get to this interesting setup where I'm doing 1, pardon me again, divided by 0, and that's impossible, which is why you have a vertical asymptote right there at pi over 2. We get to pi, we have 0 divided by -1, so the value is 0. And then right here, we have another vertical asymptote because -1 divided by 0, not definable. Then back at 2 pi, we're at 0. So tangent's interesting where we don't have a ton of information to know what this function looks like. So I want to add a little more info. So I'll split it in half because halfway to pi over 2 is right here again at pi over 4. I'll roughly put pi over 3 and pi over 6 and give us some more values. Now I should work this out by hand, but I'm going to kind of just explain it. So if I wanted to find right here, tangent at pi over 6, that's 1/2 divided by root 3 over 2. So I have 0.5 divided by root 3 over 2, and that's roughly 0.75. And so right here at pi over 6, I'm going to get about halfway on the way to halfway. And now if I do tangent at pi over 4, that's just root 2 over 2 divided by root 2 over 2. That's exactly 1. So I'm all the way up here to 1. Then what's really interesting, if I do for pi over 3, root 3 over 2 divided by 1/2, I'm dividing by 1/2, I'm really multiplying by the reciprocal. And so that would be root 3 over 2 times 2, so the 2's canceled. And the value of root 3 is about 1.73. And so I went from 1 really quickly up to 1.73. And that's how the tangent function works, where as I get closer to those asymptotes, I just take off towards positive or negative infinity. I'm going to expand this a little bit. If I wanted to figure out what it looks like over here, well, that point would be negative pi over 2. Quick reminder, or just teaching point, if I wanted to get to negative pi over 2, I can start from the origin and just go backwards. 3 pi over 2 is the exact same thing as negative pi over 2. If I wanted to get to like negative pi over 4, just start here and go backwards to negative pi over 4. But the idea is, if I wanted to find these same y values over here, they're the exact same y values, just negative. So at pi over 4, negative pi over 4 would be negative 1. At negative pi over 6, I'm at negative 0.57. At pi over 3, I'm at negative off the page. And so I get down to these vertical asymptotes really quickly. And that's how tangent looks, where if I come from the asymptotes, kind of go curved over, and then I just take off toward infinity. I'm here at negative infinity. I come through, and that pattern just goes on repeat over and over again because you have undefined values for tangent. So now I'm going to show off. Fortunately, I have to erase that, otherwise it's going to be really confusing. So I hope you got that. You can pause and take more notes on it. But let me clear all my annotations from here. And then really quickly, let's take a look at sine, cosine on a better graph than what I did. Reminder, f of x, y, same thing. But if I look at your cosine value, you can see that it starts at when x is 0, y is 1, and you can see that the top, the largest y value is 1, smallest y value is negative 1. Cosine is the same thing, but just starting at the origin. And you have tangent that at every pi over 2 interval, so if I have x equals pi over 2, you can see there's that vertical asymptote, and then every additional pi interval, so 3 pi over 2, you have another vertical asymptote, and like that's what tangent looks like on and on and on forever. This is my very last slide. I know it's long, but this is all optional, and I hope the learning's good. So yeah, I hope for that. Just a quick, what are some tangent values that might be helpful? If I wanted to know tangent of, probably should have written in the text, tangent of pi over 6. Again, that's just me dividing my sine and my cosine values there. So if I had 1/2, I'm gonna write up here, sine at pi over 6 divided by √3 over 2, what I would really do to do that is I would multiply by the reciprocal. So I would multiply by 2 over √3. So your 2's would cancel, so you'd have 1 over √3. If you rationalized it, multiply top and bottom by √3 over √3, you get √3 over 3, which is roughly that 0.75 value I had from before. I'm checking to make sure I'm not lying to you. Yeah, about 0.57 that we had earlier. And then tangent at pi over 4 is the best because it's just the same value divided by itself, because your sine and cosine values are the same there. And so that's just going to be 1. So tangent of pi over 4 is 1. And then tangent at pi over 3 is going to be equal to √3 over 2 divided by 1/2. I can do that work, I think, up here. If I had √3 over 2 divided by 1/2, again, that's really just multiplying by the reciprocal. So I would just say times 2 over 1. What's nice here is the 2's cancel. √3 divided by 1 is just √3. That's why tangent at pi over 3 is √3, about 1.73. And then you all saw from before, right here at pi over 2, it's undefined. Back over here at pi, it's 0. At 3 pi over 2, it's undefined. And at the origin are 2 pi, or intervals of 2 pi. Intervals of 2 pi, it'll be back to 0. The last thing I want to mention is just a reminder about inverse tangent values. If I was being asked about an inverse tangent value, like in the inverse tan of 1, for example, you're being asked to figure out what was the radian input value that resulted in an output value of 1, and that would just be pi over 4. Reminder that the inverse tangent relates to the original function, and that tangent of pi over 4, that input resulted in 1 for the output. So the inverse tan of 1 would result in pi over 4 for the output. Inverse functions, again, they are symmetrical at y equals x, and they just have the opposite input output as the original function. Reminder that this -1 is not an exponent, it's referring to the inverse function, which we can equivalently refer to as an arctan or arcsine or arc anything. It just means the inverse of that value. As always, let me know what your questions are. I hope you watch the parts that are most valuable for you. I'm here for you, and I'll see you all soon.